Hi everyone, my name is Aman Sharma and this is the webinar for North India chapter that basically is a part of AIOUG. We do these webinars on continuous basis, and this is basically another set of webinar that we are doing actually for this particular month. So this is basically about buffer cache, and this is basically going to be about the deep dive about the buffer cache. So this is about me. My name is Aman. I have been working with the Oracle database for quite some time. I'm an Oracle ace. I have co-authored 2 books. I have been the part of the AIOUG as I serve on the board of AIOUG as vice president, and I am the founder and the lead of the North India chapter of AIOUG. Some certifications of mine. I blog here, I tweet here. Okay, so first thing about this particular webinar is, or this particular presentation is, that these are all basically my understandings, and obviously these are basically the things which I have understood in the way I thought they are actually happening, or they are basically functioning. Of course, since I do not know exactly how the things really are going inside, I have no access to the source code or the internals as such. So basically, take whatever I say with a pinch of salt or a grain of salt, because I definitely can be wrong. Okay, so this is what we are basically going to talk about. We're going to talk about the buffer cache, and for the lack of a better bullet point, I just mentioned a little bit more about the buffer cache, and we'll talk about what exactly the buffer cache is all about, how exactly it works, what exactly it does, and some of the internals actually about it, and then how to tune the buffer cache. So the first part is basically going to be a quick introduction about it. So as we already know that Oracle database has an instance which is basically comprising of many memory structures, and these structures basically are shared among the user groups, among the users actually who are going to be using the Oracle database. So one of the components is going to be the buffer cache. Since it's a part of the SGA, the buffer cache is going to be shared among the users. Obviously, we do have the other structures as well, which are basically the physical structures. So we have the database files, we have the table spaces, we have the log files, we have the control files, and of course we'll have listeners, and they are going to be actually helping us to connect to the particular system. To basically make the database communication work with the instance, we'll have a server process, and it will also have the PGA, the standard stuff actually, which is going to be there about any particular part. Now, one thing which is going to be very important in terms of database is that database is basically going to be having a similar kind of kernel structure as what we have in terms of the network. So very commonly given example is basically the OSI model, which have different layers actually before the particular network packet is actually going to be getting to the network adapter. In the same way, we have the Oracle database actually having its own set of kernel layers through which different set of functionalities are actually going to be processed. So basically, in terms of the Oracle kernel, these are different layers which are actually going to be doing different set of things actually. So you do actually can notice that there is actually for each particular functionality a separate layer or a distinct layer present in terms of the Oracle kernel architecture. Now, obviously, in terms of the database, when we talk about buffer cache, the buffer cache is basically served by the kernel cache layer, which is represented by the KC, acronym, or you can say the keyword. Now, this particular layer is basically what is going to be serving, you can say, the functionality or the inner functionality of the buffer cache, and this actually can be a good lead to understand a couple of $X tables which basically are going to have the internal information about the buffer cache. So obviously it means that when we actually want to check of any particular table inside the particular database for buffer cache, if that $X table starts from KC, we actually can assume that it is basically talking about kernel cache, and it actually has the second character mentioned as B, which stands for the buffer, that means we are possibly looking at the buffer cache actually. So this is basically what I mentioned here. So this is actually from version 18c, that we are basically having bunch of tables which are actually going to be having this KCP as a prefix available, and as when I ran this particular thing, it was actually 30 such tables, and you can notice that these are basically going to be a different set of tables doing different set of stuff actually for the buffer cache. So now basically what exactly is buffer cache? Of course it is a memory structure to hold the data which is going to be accessed from the disk. It is going to be used to provide the data caching basically for the users, which means the data which is pulled from the disk is actually going to be cached over here. It is definitely available for single instance as well as for rack, and obviously in terms of rack it is actually going to be giving the benefit of, or you can say it is going to give the functionality of the cache fusion. And buffer cache is a circular cache, which basically means it is actually going to throw the data out when the data is not actually going to be needed. And within the buffer cache we will have different types of buffers, and those buffers are basically going to be created by different types of buffer status. So for example, we are basically going to be having the buffers in terms of free buffers, consistent buffers, consistent read buffers, or dirty buffers, and so forth. And to make sure that the buffers do not keep hanging around in the particular buffer cache and occupy space, the dirty ones are constantly going to be pushed out of the buffer cache, which is going to be done by a checkpointing mechanism, which is actually going to be happening all the time, which is basically taken care by the incremental checkpointing mechanism. Now obviously the buffer cache is basically going to support the logical IOs, which are basically going to be the IOs which are served from the buffer cache. So in terms of the logical IOs, we do have actually two kinds of basically IOs possible, consistent one and the current one. Of course the current ones are basically going to be the IOs which are actually going to be about the current copy of the particular block, which means this is the actual copy which is going to be either accessed from the disk, or this is going to be the copy which is going to be modified by the users for the DMLs. There is going to be only one current version of the particular buffer which is actually going to stay in the particular buffer cache, and this is going to be the same thing which is actually going to be there even in terms of the particular cluster environments. The particular current image is basically going to be something which will rather become consistent once you're going to give a rollback or a commit. But if you do not give a rollback or a commit, for any other user the particular consistent copy has to be created, and that copy will be created by the help of creating a CR copy, and the CR copy is basically going to be created with the help of applying the undo actually over to the particular buffer, which means using the undo image we are going to be creating a CR copy which is basically going to be given to those users who do require a consistent image to be available for the same buffer in terms of the environment. Now the consistent reads are basically going to be the reads which I just mentioned are going to be available to you in terms of your particular system for dirty buffer. So if someone is trying to read a copy which is still undergoing changes, and those changes are not yet made permanent or not even made rolled back, then those changes are basically going to be not available for any other user except the owner of the transaction. So consistent images are required to be created to basically ensure data consistency actually for the particular users, and that is basically going to be done with the help of creation of the CR copies. Now in case you want to have these CR copies to be traced, you basically actually can use the trace event 10 to 100 or 201, which actually can show you the particular such copies in terms of your systems. Obviously the CR copies are basically the temporary copies, and they are not actually going to be written to the disk, because CR copies are basically going to be the copies only required for the purpose of making the particular data accessible to the user in a consistent manner. They are not actually going to be the particular copies which are going to be required, or which are going to be later on required in terms of database. So this means this is basically going to be a particular copy which is going to be eligible for being throwable. That means once you are going to be running out of the buffer cache space, this is basically going to be available to you, as a replaceable copy. Now, buffer cache actually has been around from a long time, and buffer cache has undergone a couple of changes in the last couple of releases in the database. So before the version 9i, the buffer cache was still available, but the management of the buffer cache was a little bit different from the current version that we have right now. So the buffer cache basically in the pre-9i environment or pre-9i era basically was one big chunk of the cache which actually was available to you, and that big chunk of the cache was actually giving the size of also to your keep buffers and the recycle buffers. So the database buffer cache was basically the standard cache available to you, and in case you basically want the particular buffers to be available for a longer duration compared to the algorithm which is going to serve the standard cache, you could actually put them in the keep, or in case you do not want the buffers to be available for a very long time, you basically actually can put them into the recycle buffers. Now the only caveat in this particular part is that the default buffers cache basically was giving the size out of it actually to the keep buffers and to the recycle buffers, and this also was actually one of the major troubles, that all of these particular structures, they were not actually available for being dynamically resized. That means the changes to these particular buffers required actually a database restart, which basically is changed from 9i onwards. You still have the cache and the keep cache and the recycle cache available, but you now have all of these caches available as independent, and these caches are basically available to you in terms of the system without really requiring a particular downtime to change them. So that means they are now dynamically available, and obviously they are available to you to change even when the system is currently live. And besides the standard caches, you also have the non-default buffer caches also available, which actually will serve the purpose for those particular table spaces which are basically going to be having the block sizes which are actually not going to be of your standard block size. So besides the default caches, we also have the NK caches actually available to you as well. And a new memory management component was introduced also in 9i, which was called Granule. So we'll look at that just in a minute. So how the buffer cache is basically going to be managed? Well, we have the parameters to manage it. We have the DB cache, the keep cache, the recycle cache, and so forth. And the minimum unit of IO for the buffer cache to do the work is going to be the DB block size. The DB block size, as you already must be knowing, is going to be either of 8 KB or whatever size you're going to be setting up while database creation is going to be happening. You are going to be setting it up one time. It's not actually a changeable parameter, and this is basically going to be applicable to your entire buffer cache. Now obviously in terms of the older environments, the DB block buffers was basically the parameter which was there to manage the buffer cache size, and this parameter is still around, but it is not something which you should be actually using basically for the buffer cache configuration. So basically you should be actually using the DB cache size parameter only. The DB NK cache is basically going to be there for the non-default caches if you actually want to configure them. Of course, they are not needed until unless you're not going to be having non-default block size table spaces also available to you. Now the subpools which are basically created basically for the buffer caches are actually going to be there. The keep cache is basically going to be the cache which is controlled by the DB cache parameter, and this is something which is possibly going to be recommended when you're going to be requiring the particular objects buffers to be kept for a longer duration as compared to your particular default cache. it is not a part of auto-tuned auto-tuning mechanism, which means the buffer cache is not really going to be tuned by the auto-tuning parameters like SJ target or memory target and so forth, and it is basically going to be keeping your buffers for a longer duration, or you can say for almost all the time. The other structure or subpool of the buffer cache is going to be the recycle cache, which is basically going to be the cache which is going to be not keeping the data for a very long time, and it is ideally suggested for those environments where the particular data is not going to be needed by you more than the time of the duration of the query's execution. That means once the particular once a particular query is over, you do not really want the buffers of that particular query's objects actually to stay in the memory. And again, this is also not going to be about auto-tune, and it will be actually not really going to be requiring any particular auto-tuning mechanism in the system. The NK caches, of course, are actually going to be there, and as I said, they are basically meant for the transportable table space mechanism, which is obviously going to be needed only if you're going to be setting up the non-default block sizes in your environment. Now, we talked about granules briefly. The granules basically is a memory component, and we're going to talk about it now. So basically what is going to be a granule? It is actually going to be a memory chunk created to actually give the sizing to different memory structures within the SGA. It is represented in a couple of internal tables over here, and as you can see, it is served by different layers of the Oracle kernel, and granule size is basically going to be set internally by Oracle depending upon your SGA size, which means basically about your SGA, that whether it is going to be 4 megabytes of granule or 16 megabytes of granule, that will actually depend that how much big your SGA size is actually going to be. Now, granule basically is actually going to hold the particular memory components of different memory structures in your system, and this is actually a query which you possibly can go ahead and use actually to see that which component of the SGA is actually having which type of the granule actually available to you. So you can actually see that this is basically an example of different memory structures actually in the system, which basically have the chunks of granules available to you, and there is a linked list sort of which is available to you in terms of the memory, which is telling you that how the particular structures are basically going to be having their next granule available to them. Now, the schematic of the granule basically is actually going to hold the information for the data blocks. So the data blocks basically are going to be the blocks which are going to be on the disk, and for each data block which we are basically going to be having in the memory, Oracle is going to be creating something called a buffer header. So basically what a granule actually does, it actually holds the arrays of the buffers for your particular data blocks, and those particular buffer headers arrays are actually going to be used by the system to decide that the buffer is a hot buffer or a cold buffer and so forth, and all the linked list actually in terms of the buffer cache are basically going to be comprising of these particular buffer headers. So this is basically going to be, you can see the information part available. So there is going to be a header for the granule, and for the particular header of the granule we are basically going to be having a couple of buffer headers and data buffer arrays available to us. Now, the buffer cache is basically going to be made internally in terms of a hash table. So basically what Oracle is going to be doing, it is actually going to be creating for every block accessed a hash key value pair, and that key value pair is basically going to be used to maintain the information of the particular buffers inside the buffer cache. Now, this is particularly done by the help of this address, which is called DBA, standing for data block address. And data block address is basically going to be a number created with the combination of your file number as well as the block number. So this address is basically a key value pair, which is actually going to be a part of a hash table, and that hash table will have multiple hash buckets, and those hash buckets are basically going to hold the particular buffers of different segments. So obviously the particular hash buckets are going to be holding the buffers with some chains, and those chains are going to be called hash chains, and those hash chains are sort of like the chains where the buffers are actually going to be sort of like hanging over them. So this is basically going to be the mechanism where it is actually going to be decided whether the buffer can stay in the buffer cache or not. And to maintain this kind of mechanism, we basically have two latches in the system. One is called the cache buffer LRU chain latch, and the second one is cache buffer chain latch. One latch which is basically used to actually move the buffers inside the linked list, and the second latch is basically used to hold the buffer and use the buffer basically for the access. So how does the particular mechanism of this is actually going to be done? The hash table is created inside the buffer cache, but the number of hash buckets are basically created based upon the size of the buffer cache. Of course, if you want to manually control it, it is possible with this parameter, but as always it is actually not a good idea to change any internal parameter by yourself. Now this is actually going to be a sort of schematic which is going to be there about the buffer cache. So buffer cache is going to hold many buffers. So basically these buffers are going to be a part of a hash table, and hash table is basically going to be having multiple hash buckets, and each bucket is basically going to be having the buffers available hanging from different hash chains. And obviously you can see that for the particular buckets to be managed, we will have something called the buffer cache chain latches, and these latches earlier were basically available to manage one bucket by one latch, but now the mechanism basically is to manage multiple buckets actually from one latch. And obviously if you want to change the number of the buckets, or if you want to control the number of the latches explicitly, it is possible by these parameters. Now buffer cache is created by these particular structures inside the system, which is basically what we're going to discuss just in a minute. So obviously the buffer cache is basically going to be available to us in terms of different set of pools, and we mentioned that we have the default, keep, recycle and all such structures available. Of course we actually can create non-standard block sizes available, non-standard block sizes pools also available, but that obviously is not needed unless we are not using a non-default block size table space in our environment. Now the major thing in terms of the buffer cache, or the major movement of the data within the buffer cache, is going to be happening with the buffer header, or you can say within the buffer pools. So each buffer cache is basically or each buffer cache substructure or structure is maintained by something called a buffer pool. So buffer pools are basically available to you or exposed to you in this particular table KCP WP BPD, which is basically kernel cache buffer work area buffer pool descriptor, and this is basically going to be having the information about the granules, which are basically going to holding up the buffer cache buffer headers, and these granules are basically going to be comprising in terms of something called work areas. So work areas are basically the divisions of the buffer cache into smaller chunks. So this is sort of like what is going to be happening, that we'll have a buffer pool, for example a default buffer pool which will have multiple granules. These granules are basically going to comprise across multiple work area sets, and as I said, the work areas are basically going to be different chunks of the buffer cache, and these work areas are basically used or maintained by different DB writer processes, which means there are going to be DB writer processes which are actually going to write from multiple work areas into the system. So that means the number of DB writers are basically going to be maintaining their own set of work areas in the environment. Now the buffer headers are basically the meta structures, which means they are basically going to be the structures which are going to load your buffers actually into the buffer cache, and that is very important, because the actual buffers are basically going to be maintained with the help of these particular buffer headers. So basically buffer headers, they will have the information of the buffer or the address of the buffer. Buffer headers are going to be the part of your hash chains, and they are basically going to be moved around in terms of different linked list within the particular buffer cache, and they will actually maintain the status information about the buffers, whether they are being dirty or CR or free or clean or pinged and whatnot. And that is why it is important to note that the buffer cache is not exposed in terms of something called the $BC. We actually have the buffer cache exposed in terms of $BH. So $BH basically is the table that is actually going to be the particular table for the buffer cache, and that is basically the buffer header table actually. So basically the work areas in terms of the buffer cache, as I mentioned, are basically going to be the divisions of the buffer cache available, and this is basically going to be a good thing that in terms of a larger cache, we actually will be having trouble to basically find our required buffers. And basically for that reason, the buffer cache is going to be divided into smaller substructures, or you can say smaller chunks, and those smaller chunks are basically going to be your work area sets. Work area sets are basically going to be managed by your particular latches, which are going to be the cache buffer LRU chain latch, and these latches are basically going to maintain the information about that how the particular buffer movement inside the buffer cache is actually going to be happening. So in case you want to check a particular buffer, whether it is a part of your buffer cache or not, that is actually available to you through this particular latch. So each buffer cache, each work area is basically going to have its own set of linked lists in terms of the management, and it is maintained by the table $KCB WDS, and I believe it is going to be created by this mechanism of CPU count divided by 2. So it basically means you're going to be having 10 CPUs, you're basically going to be getting 10 by 2, that means 5 work areas. Of course this obviously can change, and you should test actually what the version actually is doing for you in terms of the work areas. Now, a very common understanding about the buffer cache is that the buffer cache is basically maintained by this set of particular linked lists. So we have a so-called LRU list and a so-called dirty list with something called as a hot end and something called as a cold end. And these are some of the common terminologies used to explain the buffer movements within the buffer cache, which is okay to in a certain extent, but that is not entirely correct. So basically in terms of the buffer cache, the actual linked list that we have basically is, we actually have a linked list which is called the master, or you can say the main linked list. This linked list is actually going to be the list which is basically going to have all the buffers available to you, as a starting point. The buffers from this particular linked list actually can move to another linked list called an auxiliary list, which is basically a aux list, which is actually going to be your so-called cold list. And in case the particular buffers are going to be made dirty, they can be a part of your CKPTQ list, which is actually going to be 2 in number, which means in one list the buffers are actually going to be attached, and in the second list or from the second list the buffers are actually going to be written actually in terms of your disk. So the hot end and the cold end actually are not in terms of one linked list, but they are actually available to you from 2 linked lists in the environment, and obviously you actually manage them through the chain latches, and that basically are going to be used to access a buffer or move the buffers to and fro from different set of these particular linked lists. Obviously you can change it also if you want to, and this is the structure which is basically available to you across all the particular work area. So you can actually see that we are going to be having one particular work area which contains these particular linked lists, and the similar linked lists are available to us across all the particular work area sets in our buffer cache. So basically the linked list in the buffer cache, if you really want to see, are actually going to be exposed in terms of the table $KCB WDS, which is basically going to have the main list exposed as the next and PRV replacement list, and the auxiliary list exposed as the cold list. And basically this is basically going to be the set of the columns which are going to explain or sort of like going to show that the buffers are moving from the main list to the aux list and so forth. Now, the particular linked list in every particular work area sets are actually going to be these ones, and this is the dump of the buffer cache which I have done, and this particular buffer cache dump actually does show the particular header of a buffer. It does show that in which particular linked list the buffer is actually a part of. It actually shows the hash chain in which the buffer is a part of. It actually shows the count of the touch of the particular buffer, and obviously we can actually see that all these things basically are actually shown to us in terms of the buffer cache in the buffer dump. So obviously when we talk about the buffer cache, it is definitely not possible that we don't talk about the algorithm through which the buffers are maintained in the buffer cache. And the buffer cache algorithms which are maintained are actually three basically. So a very commonly used term is basically the LRU, but the buffer cache has gotten different variations of this LRU algorithm that we're going to see just in a minute. So the first algorithm which basically came for the buffer cache or initial versions of the database basically was the actual LRU algorithm, which was pretty simple. So basically you had a single linked list which obviously did have an LRU end and a MRU end, and basically this actually did bring the concept of this hot and cold buffers. And this particular structure was basically good because if a buffer was very highly accessed, it actually was promoted to the hot end, and if the buffer was actually not used, it was actually on the bottom of the list and it was actually considered as a cold buffer. Now this did not serve very well when the databases started to become bigger, because the tables, which possibly are going to be very large tables, those tables actually can flood the entire linked list with their own particular buffers, which means now the other particular buffers in the linked list are going to be thrown away. And obviously this needed some tweak, and this tweak came in the version 6 as the modified LRU algorithm or V2 version of it, which basically did a small change that for such kind of full table scans happening for larger sized buffers or larger sized tables, Oracle created a small window, or you can say a small chunk actually, which was called the FTS window. And this FTS window, or basically the full table scan window, is actually going to be used only for those buffers which are going to be a part of your full table scan. And this particular window is actually controlled by the particular parameter small table threshold, which is going to be 2% of the database buffer cache, which was again fine. That means you actually could have the other set of things available to you in terms of the standard cache, but it also did create the trouble that you possibly are going to be using it for other structures which are really not going to be taking the best of this particular LRU algorithm properly. So in terms of the modified or you can say remodified version of this, Oracle implemented something called the midpoint insertion algorithm. So instead of actually creating this FTS window, they basically divided the linked list into two parts. One part which is sort of like going to be the hot end, and the second part which is basically going to be the cold end. And the buffers are basically attached into the midpoint of this particular buffer window, and that particular midpoint basically sort of like formulated the name of the particular linked list, or the algorithm, as midpoint insertion algorithm. So basically what happens, every buffer is actually going to be accessed, and whenever the buffer is going to be accessed, it is actually going to be incremented by a particular parameter, which is going to be the touch count. And the touch count is basically going to be the count which is given to the buffer to understand that whether it is actually accessed or not. Higher the touch count, the buffer is considered to be hotter. And the touch count is incremented in a 3-second timeout, which basically means the buffer has to be actually accessed after 3 seconds for the count actually to increase. And this count is available to you in the particular table TCH, which is basically the touch count column. So basically what is going to happen that within 3 seconds the counter does not increase, but after 3 seconds the counter does increase. And if the counter is going to become more than or 2 equal to 2, it is basically going to promote the buffer to the hot end of the chain. Once the buffer comes to the hot end, the algorithm is basically going to sort of cool down the particular buffer explicitly, and once the particular buffer becomes cooled down, the particular buffer is explicitly attached to the cold end. That means it is going to be made very hard for the buffer actually to stay in the buffer cache as a hot buffer, because it is going to be artificially cooled. And this is also going to serve the purpose that just for the sake of this, that once a buffer was a hot buffer, Oracle will not actually make it possible for the buffer to stay in the buffer cache as a hot buffer for infinite period. It has to earn the right for considered being a hot buffer explicitly again and again. So this is actually going to be a much better thing, and it is controlled by these parameters. So you can see that the buffer cache is divided in terms of the hot and cold by a 50-50 nature, which is controlled by the first parameter. The buffer is considered to be hot if the counter is equal to or more than 2. If the buffer is basically going to be cooled, it's actually going to be set up in the counter as 1. It is going to stay in the particular buffer cache with the value 0 once it's going to be becoming explicitly cold. And the touch count timeout is set by the parameter touch time, which is going to be 3 seconds, and the CR buffers are not actually going to be a part of your buffer cache, so they will be actually thrown out, which is by default. So all these parameters are basically having by default these values. Now there is a term that is there that we can actually use a clause called a cache clause to basically cache the buffers explicitly also in the buffer cache, though that's not entirely true, because basically what the cache clause does, instead of putting the buffers into the midpoint, it actually puts the buffers onto your hot end. That means by default the buffers go into the midpoint, but actually with the cache clause the buffers will actually go to your hot end directly. But explicitly the buffers, whenever they're going to go into the hot end, they are still going to be made cold, and that means they are still going to be replaceable. That means the cache clause actually doesn't do what it actually says, which basically means it doesn't really cache the tables permanently. Now in 12c or from 12c onwards, instead of having just the touch count based algorithm, Oracle also have something called a temperature based structure, which basically is going to be for the objects which are going to be very large in size. And the idea basically is that instead of maintaining larger tables in terms of the counter based or touch count based pointer, they are basically going to be maintained by a temperature thing. So that means you are actually going to be having a smaller chunk of the buffer cache possibly dedicated towards this temperature based caching, and you can actually use this temperature based caching actually for those tables which you are going to consider as going to be big tables. Obviously you are actually able to see the temperature of these particular tables, and the temperature is going to increase if the buffers of such tables are actually going to be accessed again and again. So now in terms of how the buffers are basically looked in the buffer cache, this is how it's actually going to happen. So simply Oracle will find an execution plan. It is going to find the extents of the segment. It is going to find the block address, which is going to be part of the hash table. It is going to find the buckets which are going to be keeping that particular hash table. It is going to find the latch basically to access that particular buffer, and with the particular buffer is found, that means it's going to be a logical IO, and if the buffer is not found, it is actually going to be unpinning the latch and basically going to do a physical IO to get the buffer read from the particular disk. And depending upon whether the buffer is possible to be read directly or we needed a free buffer to be available, we are going to be pinning the LRU chain latch and basically load the buffer into the particular buffer cache, and eventually the buffer is actually going to be returned to the server process, and that means returned to the user. Now in terms of the buffer cache tuning, it's actually not really going to be very hard, because the major goal of the buffer cache is nothing but to make sure that the buffers are available, and that is basically going to be something which actually is possible if you are going to be having the proper size of the buffer cache. But still, there are going to be certain wait events which are going to be there in terms of the buffer cache. So the first one is a free buffer wait. Very simple. The free buffer wait basically is that you want to load the buffers from the disk to the cache, but the buffer cache is already occupied by many dirty buffers, and that means we do not really have the buffers free available in the buffer cache, and that means the DB writer cannot wait for the checkpoint, and it is going to start writing the buffers immediately into the disk by being into something called a panic mode. And that means the server process, which is waiting for the buffers to be loaded into the buffer cache, now has to wait for the time period till these buffers are not going to be made available to you free in the particular system. So obviously it means that the time period is basically going to be the time period for which the server process will log the free buffer wait. The other waits are going to be the common waits of the user IO class, the sequential, the scattered, and the parallel reads. These waits are basically going to be the waits not happening in the memory but happening from the disk, which basically means that the particular waits, if they are being shown to you, that means this is actually going to be the time taken by the process to read the data from the disk to the cache. And if these wait times are not actually going to be more than 15 milliseconds and constantly increasing, it is really not actually a problem. But if it is actually continuously increasing, and it is increasing more than 15 milliseconds in your environment, that does mean that either the particular queries are basically being slow due to the disk, and possibly you need to do something on your disk, like adding maybe a bigger disk, or better, not bigger but more disk actually for bigger bandwidths, and obviously maybe adding even the buffer cache size so that you possibly can hold the buffers to a much larger time in the buffer cache. Latches usually will not actually have contention and do not really require indirect tuning, because they are automatically set by the system. But obviously you still can do certain things, like if you do notice that there is a lot of CBC chain, LRU chain latch contention, that means the size of the buffer cache is not enough. You possibly are using the LRU chain latch a lot actually to load the buffers and find the buffers for your query in the system. That means you possibly want to increase the buffer cache size. And if it is going to be the CBC latch or the chain latch in the contention, that means you're trying to find the buffer a lot actually from the buffer cache, and that means you possibly are going to be either reading a lot of data into the memory which you're trying to search, or possibly you are going to be actually having a suboptimal query. So either you possibly try to tune the query, or possibly try to, if you're using indexes, try to use indexes which possibly can be using something like reverse key or global hash partition indexes, which can put the burden a little bit lesser on your particular buffer cache. So obviously, if nothing else works and if nothing else is actually there, then you definitely can increase the buffer cache size explicitly. But if you're using the automatic memory management or SGA target, this is going to be automatically taken care. The buffer busy wait is basically going to be the wait where when a buffer is already used by a session, the other session is actually going to log for it. And this is basically going to be one of the major troubles in terms of the system possibly. The buffer busy wait is actually going to be happening for different types of the buffers in the environment. As you can see actually that there can be different classes of these buffers available. There are about 14 such classes available, like data block, segment, header, undo header, first level bitmap, second level bitmap, and so forth. So you do need to check actually that what kind of wait or what kind of buffer class wait is actually happening for you, and then decide possibly that what is actually going to be happening in your environment for that kind of buffer. Now you can actually notice that here it is basically shown that a buffer busy wait is happening, and there is basically different set of classes available to you in terms of the buffer cache. A kind of a very old terminology or hypothesis is a hit ratio, which basically is that in case you're having the buffers available in terms of your system from the cache, that means everything is given to you, or mostly the things are given to you from the memory. That means you have a very high hit ratio, but it is not really actually a very good marker for a tuned database, because hit ratio can be artificially low or artificially high For example, if you're doing a lot of reading of the similar types or similar buffers of a segment, it's actually going to increase the hit ratio explicitly. Or if you're doing a random selection of the buffers, that means the buffers possibly may not be found in the buffer cache next time, and that means the buffer hit ratio possibly can be low. Obviously, if it is consistently being low and you are suffering from the performance issues, it is possible that you might increase the buffer cache size, but otherwise hit ratio is not possibly going to be the right goal for the tuning in terms of the buffer cache. Obviously, as a DBA, there's not much to do. Like I said, you basically have to just make sure that the size is going to be enough, and you do not really need to worry too much about the physical IOs, but you should actually pay attention to the logical IOs. Reason being that it's the logical IOs which are going to put the contention for latches in the buffer cache, and that is actually going to be the main concern for you. Other than that, it should be just the memory management which is actually going to be there, and which is going to be taken care by the automatic memory management, or the automatic shared memory management already. Obviously, if you can avoid the buffer cache, like you can use direct path read and so, that is also going to be helpful. So obviously the best part is you let system actually decide it. Better is you can actually use the DB cache advisor to understand that do you really need to increase the buffer cache, or it is actually going to be any help for your system or not. And obviously AMM or ASMM are actually going to make the buffer cache functionality much better, because it's actually going to be taking care of this by itself. So in case you want to get more detailed about buffer cache, you actually can use Aura debug, and you can basically get a lot of information about it. But it is actually like a rabbit hole. It's not really documented. A lot of things are not documented, so it is going to be a lot of fun exercise, but it is not actually going to be something which you should really be attempting to do, because you might actually get hit into a dead end kind of situation where you might actually have figured out something, and it possibly could be correct, possibly could not be correct. So as always, do it completely just for the sake of fun and just for the sake of learning more about the system. Obviously, that's what I said, be crazy and have fun. Some references for the particular internals, and you actually can check out these particular books which are going to be helpful. And that's pretty much going to be about this particular webinar, everyone. As always, hopefully it was useful, and it is going to be helping you out to understand the buffer cache in more detail. For any questions or for any comments, do hit us in the comment section. And also for other webinars that we have done in the past, do check out the playlist of the same. We do also post quick tip series videos, which are smaller videos, and I just posted 2 videos about the database 19c installation, and the other small quick tip series are also there in the playlist for that. So do check that out as well, and do subscribe to our YouTube channel. Thanks a lot, and my name is Aman. I'll see you in the next webinar series, hopefully very soon. Thank you.